Hello everyone, I'm Dominic and my project is using search algorithms to solve a Rubik's Cube. There's a lot to go over. I have 5 to 15 minutes. I'm not trying to waste anyone's time. So let me just start off. Here's a Rubik's Cube. We can apply 18 different moves, clockwise, counterclockwise, to all these surfaces. So that leaves us with a branching factor of 18. And so here is the algorithm that is inspired that I'm using, but also using the implementation from Ben Belarus, who also used course algorithm. The Corf is probably developed one of the more optimal ways to solve a Rubik's Cube. And so one of the problems that we have with a Rubik's Cube, and especially with a search algorithm, is that at one move, we have 18 different combinations that can happen, right? So one, like these are all one moves being applied to it. So it's 18 to the power of n being the amount of moves. So as you can see, at a depth of 6 moves, we're at 7 million, then 100 million, and then 1 billion, and then again, it's exponential. So it will take forever. IDA star again is going to be the more optimal way to do it, but Corf originally, how the way he did it was using the corner pieces and using more of a distance between the corner pieces to their goal state. So one thing I did want to know, I'll get into later, is that we're going to be using a pattern database. So, quote from Corf: while we normally think of a heuristic as a function computed by an algorithm, any function can also be computed by a table lookup. Given sufficient memory, in fact, for reasons of efficiency, heuristic functions are commonly pre-computed and stored in memory. So this is something I definitely learned in my journey, is that I didn't really know that heuristics can be used from table lookup or a database. It does make sense. Um, Again, just trying to go through this quickly. I'm just going to demonstrate my code. If I have enough time, I'll get into the implementation of it. But here is IDDFS. IDDFS is going to be iterative deepening depth first search. So it's just a combination of depth first search and breadth first search that we're familiar with. So it performs depth first search with increasing depth limits until solution is found. So it starts with a depth limit of 0 and performs depth first search up to that depth limit. If no solution is found, it increases the depth limit by 1 up until the max depth, and then it just processes until a solution is found. And so one of the things about Rubik's Cube is there's something, again, this brings a lot of mathematicians into, because we're dealing with matrices and they love math, is that they found that the amount, also, sorry, to back up real quick, I just wanted to show you how big a Rubik's Cube can be in terms of the combinations. It is 43 quintillion, right? But it can be solved in 20 moves. So again, that's called God's number. So the IDA side is going to be using God's number, the amount of moves to solve the Rubik's Cube. My IDDFS, I'm just going to set the depth to 15. Again, I'll show you here in a little bit. So here's IDDFS. So we just have the depth, we iterate through, and we set the result to be DFS from the root. The root is just going to be the cube representation, the given depth. We go to DFS, and if the depth is 0, meaning we're at initial state, just return. Else if we iterate through the possible moves. And so I was saying we had 18 different moves, but for IDDFS, to limit the branching factor, I only took up, down, right, left, front, back, counter, and clockwise. So we make a child node, we apply that move to it, and then now we perform DFS again recursively of the child with decreasing the depth, right? And then so we go back here, we iterate through the next step, and it just keeps going. So again, it's using DFS, but in a combination with BFS. So you'll see the problem with this. So very simply, again, here is more of an interface. Here's the string representation of both cubes. Here is just a cube side by side, and then these are the same cubes, by the way. This up, left, front, right, back, down. Again, I added it so the user can choose, but for this demo, I'm going to be displaying both. So if I apply the move front, right, it just turns the front face, and I solve using IDFS, right? I set the depth to 15. I don't need to because it's only 1. You can see it only took 0.001 seconds, and I found a solution. And here's my solution. It is F counterclockwise. So I apply F counter, and again, we get the solve move. I'm not going to iterate through all the moves, but I will show you let's do 3 moves. So front, right, back, solve IDFS. 0.08 seconds, right? A little slower, but barely. So we apply the moves, and I go back counter, right counter, and front counter. And here is our solved cube. Now I'm gonna bump it up to 5 moves. So let's do right, right, front, left, down, solve, set the def. Now this is where we get problems, right? Because again, we will find a solution, but again, the problem, and I'm just gonna copy paste the solution here so I don't have to keep looking back up. So as you can see, we went from 0.08 seconds to 4 seconds, going up to 5 moves, so it's exponential. So let me just apply the moves that were given from the solution. Here we go, we have our solved cube. Now when I go to 6 moves, you'll see what I am talking about. Let's apply 6 moves to this. Front, left, down, down, up, right, back. We solve, set the def. And I'm not going to bore you. This will take forever because, again, to iterate, at 5 moves, we're only at 500,000, right? And a computer can do that, but we bumped it up to 7 million, and then 7 will be 100 million, and then it goes to a billion. So as you can see, this is inefficient in terms of solving, and it will take us forever to, if you scramble the cube up more, again, this, my computer will probably expire before it solves. So that is where IDA star comes into play. So let me restart the program because I don't want to bore you with solving that problem. So again, IDA star. If I have enough time, I'll get into it, but let me just show the demonstration. I will say, let's just go over it real quickly, the best I can. So I'm using Ben Belarus implementation of a cube. I did have to modify it a little bit to get it working. It's the same kind of representation of my cube, but again, we can just say the state of it, and then it takes the string here and then builds the matrices from it. So here we build a heuristic database, which basically just applies the moves at how many moves. So if I move right twice, then that'll be 2 moves, and it puts it into this heuristic JSON file. It could also be a text file if you want to, but this heuristic database, as you can see, has over 10 million lines, right? It's almost a gig worth of memory. So of course, trying to build a heuristic containing all 20 moves you'll need a supercomputer that's forwarded by like 500 years in the future. So search, right? Again, we're dealing with a heuristic, so we just find the best action, and we're given our state and our G-score. G-score initially is just going to be 1. Here it's going to apply to moves. If it's solved, then we append the moves. Then we return true, we found a solution. Else, we're going to take the H-score, which is just going to be the search up of our heuristic here. And so again, as you saw from the JSON file, it's just a string with the corresponding amount of moves that it took to it. So, and then F-score is going to be G-score plus the H-score. Initially, again, G-score is going to be 1. So if the F-score is less than the min value, then the min value is going to be the F-score, and we take the best action and we put it in here. Else, if it is equal to the min value and we don't have any best actions, then we just store it in there. Else, we just end it. We take a choice of our best action. Again, this is also just a limiter, limiting the threshold, the amount of moves that we can apply to it. And then we just append the next action to it, and then we recursively call search again with the new added action that we added, or the state of the cube with the G-score plus the minimum value. And so let me just get into it. So as we saw, right after 6 moves, that might take a few minutes, that might take a few hours, depending on how we have to traverse the tree. But with IDA star, we left off at 6 moves. Let's do 6 moves. 1, 2, 3, 4, 5, 6. Right, and we solve using IDA star, and it gives us our solution. Here is our solution, and as you can see, what would have taken many minutes actually took us only 0.002 seconds. And so let's apply these moves. So back, back, right counter, front counter, left counter. All right, typed it in wrong. Down counter. As you see, we have a solved cube. So now we are overcoming the time it took exponentially to solve using IDDFS using IDA star. And so again, I could show you we could apply many moves to this. We could apply over 100 moves and it'll still solve it. So I won't bore you with that, but let's just do a few moves. So let's down, left, front, back, right, right, front, left, backwards, down, up. Just applying moves, and let's solve IDA star. It's gonna take some time. But again, sometimes it can get stuck, like IDDFS. But we did find a solution. It took us 13 seconds, and here is our solution. And I will apply that to show you that it is working. So back counter, down counter, up counter, left, front counter, right counter, right counter, back counter, left counter, right counter, down counter. As you can see, we have a solved cube, and again, this is just the more efficient way of solving a Rubik's Cube. It's one of the more optimal ways. There's a lot of different ways and approaches to do this, but again, I feel like this is more simpler. So Corf again uses more mathematics and to calculate the corner edge pieces and their distance away from their original face. But just by taking the string and building a database with the amount of moves that it took to get there, we achieve the same results. And that is the gist of my project, being able to solve the Rubik's Cube, showing kind of more of a blindly approach like IDDFS. Again, there's no heuristic, it just follows, it just goes to one node to the next at a given depth. But by using a heuristic and a heuristic database, we are able to solve a multitude of any moves, and we're not going to see it be as exponential as IDDF. Thank you for listening, and that was my project.